Well, yeah, exactly. You'd face this, generally speaking, n equations, they're usually nonlinear. It's a real hassle. But theoretically, you can do this. You can say, well, really, to a first approximation, I'm trying to solve this one. The Jacobian of f at x naught, let's say, times x minus x naught. So if I'm, and if I also know that y at x naught is equal to y naught, right? If I have that initial, if I know that point, if I know that y naught is the image of x naught under f, then I can try to find an inverse for the function near that data. And so my first attempt is to take the linearization, right, and solve for that. Solve that for x there. Ah, yes. So, yeah, you're getting closer to it. I'll say just a little bit more, and then we'll stop for today. But that's exactly the idea. So the thing is, to solve for x here, you've got a matrix times a vector, right? So what you have to do is you have to multiply by the inverse matrix. And so that gives us straight away x is equal to x naught plus the inverse matrix of the Jacobian at x naught times, well, y minus y naught. And then you do something like t of y is equal to x naught plus the Jacobian, the Jacobian f inverse of x naught, times y minus y naught. And that's how you iterate. You do it again. And you can just keep doing this, something like that.
This is probably a dumb question, but is the generalized Jacobian matrix always invertible while only dealt with?
Oh, no, it is not. Okay. So if the Jacobian matrix is invertible, then near the point, you can find an inverse function.
Oh.
This is called the inverse function theorem.
Oh, well, you mentioned the way, yeah.
Mm-hmm. And so, like in one dimension, the inverse function theorem is just if the slope of the graph is non-zero, then you can locally invert the function because you're not at like a max or a min point, right? So now, this is not one of those if and only if deals. Like there exist multivariate functions which are just not differentiable, right? So they're still invertible. It's just like you can't apply the theorem there because the derivative doesn't exist for whatever reason. But I can say this much. If the derivative exists, in the sense that the Jacobian matrix exists, and better yet, all of the partial derivatives inside the Jacobian matrix are continuous at the point in question, x naught, then yes, we can find a local inverse for that function. And more than that, we could construct the local inverse by a contraction mapping based iterative procedure. And you also, so like a lot of the, the thing about the contraction mapping for me, it's not just like, oh, there exists something, it also gives some sort of like at least theoretical procedure for how you produce it in some kind of limiting. Now, pragmatically speaking, it's not a good way to calculate things for a lot of, it's not usually a good way to calculate things, but theoretically, golly, it's a wonderful way to like find out that your solution has a property that you'd like it to have. So I think the theory of numerical methods is awash with these contraction mapping arguments. I haven't taken the class, so I'm speculating, but I'm pretty sure. I learned all this stuff teaching. I didn't learn any of this in school. So, but anyway, I'm sure I'm over my hour now. Don't tell my wife, oh no. Oh, yeah. Well, I hope the audio was okay today. Sorry, Audrey, this is where it ends.